Hello everybody and welcome to the first video for Chapter 6. This video covers Section 6.1, which is a brief introductory section, and then we'll spend more time in Section 6.2, which is building some terminology for the rest of the chapter. Chapter 6 is about the mathematics of touring, and in particular we will be solving problems that are called traveling salesman problems. So just to give you a bit of perspective, remember that in Chapter 5 we solved what were called street routing problems. And the tool that we used to do that was a graph, of course, but more specifically, we used the concept of an Euler circuit or an Euler path inside of the graphs, and that concept allowed us to solve street routing problems. So if you are a security guard on patrol, or you are in charge of planning a parade route, or whatever, we now have the tools to do that by taking your neighborhood, abstracting it to a graph, and then trying to find an Euler circuit or Euler path. If there was no such path, then you could Eulerize or semi-Eulerize depending on the context. The main thing to remember from Chapter 5, though, is that an Euler circuit or an Euler path, the focus was on edges with those kinds of paths. You wanted to walk each edge exactly once if possible. Okay, now in Chapter 6, we're not going to focus on edges anymore. We're going to instead focus on vertices. So in Chapter 5, we studied what were called Euler paths, and those were paths in which we walked each edge exactly once. Now in Chapter 6, we're going to do the same thing, but with vertices. We're going to be looking for circuits in which we hit each vertex exactly once. But we no longer care about hitting each edge exactly once. When you shift the perspective from edges to vertices, you get what's called traveling salesman problems. So let's dive into a few examples of traveling salesman problems, and then we will move on to the tool we will use to solve those problems, and the tool is called a Hamilton path. And this is in contrast and comparison to an Euler path. So Euler paths are used to solve street routing problems. Hamilton paths are used to solve traveling salesman problems. So what is a traveling salesman problem? Well, the quote, traveling salesman is a convenient metaphor for many different real-life applications. And of course, there aren't too many traveling salesmen around anymore, but this is still sort of the canonical example of the kinds of things we will be doing. The next few examples illustrate a few of the many possible settings for a traveling salesman problem, starting with traveling salesmen themselves. So we have a traveling salesman named Willie. Willie has customers in 5 cities, which we'll label A, B, C, D, and E. What Willie needs to do is he needs to schedule a sales trip that will start and end at A, because that's where he's from, and goes to each of the other 4 cities once. So he needs to plan some sort of route. He needs to plan a travel path. And in this travel path, he needs to hit each city exactly once. He doesn't want to revisit a city because he's already sold things there. So we will call the trip Willie's Sales Tour. Other than starting and ending at A, there are no restrictions as to the sequence in which Willie's Sales Tour visits the other 4 cities. So this graph shows the situation here. So he starts at A, so here he is, he's thinking about money, and this graph represents the cost to get between any 2 cities. So you can get from city A to city D if you want to, and that will cost you $174. You can get from city E to city B if you want to, via this edge, and that will cost you $200. So basically this graph is showing you that between any 2 cities you can catch a flight, and it's showing you what the flight is. Or maybe it's showing you car rental cost, whatever. So again, to go from A to D costs you $152, so that might be what it costs to rent a car or to fly, whatever. Now in general, to get from one city to another city, like to go from, I don't know, Columbia to St. Louis, there are many ways you can do that. Right? So in theory, there are like multiple edges between A and E. But the reason we draw the graph with just a single edge is we assume there's some unique, cheapest way to get from A to E. So, you know, to get from Columbia to St. Louis, presumably the cheapest thing to do is to drive I-70. Now, you can drive a bunch of country roads if you want to, but you're going to add all sorts of mileage to your trip and therefore add to your gas cost. So between each city, we're only going to list the cheapest possible route between them. So what this graph is showing you is to get from A to D, you might be able to do it all sorts of ways, but the cheapest way is 152 bucks. Okay, now with all that being said, what Willie wants to do is he wants to walk through this graph, and he needs to visit each vertex exactly once because the vertices represent the cities. So he wants to start at A, walk through this graph, so he visits B, C, D, and E, and then gets back to A. And of course, he wants to do this in the cheapest possible way. So for example, he probably shouldn't do something like, well, okay, from A to E, and then from E to B. He probably doesn't want to start like that because then he's doing this $200 cost edge, which is the largest cost in the graph. So he's probably never going to want to travel directly from E to B when he's taking his walk. But, you know, look at this, this 120 edge right here. If he can walk that edge, that would be nice because $120 is really cheap. So the question is, can you give me a path through this graph that minimizes Willie's travel cost? Here's another example of a traveling salesman. In this case, you don't have a literal salesman, you have a satellite. I guess that's what we're calling it. Anyway, you have a satellite that's on a mission to collect rock samples from moons. And it's going to visit Callisto, okay, I don't know how to pronounce these, but G, I, M, and Titan. And the first three are moons of Jupiter, and the last two are moons of Saturn. It's going to collect rock samples and then return to Earth. So this slide here, this image here, shows you all the different times to get from one moon to another. So if the satellite wants to travel directly from Titan to Io, it's going to take 5.1 years. If the satellite wants to travel directly from G up to Mimas, that's going to cost 5.7 years, etc. Getting from Earth over to G takes 3.2 years, from Earth to Titan takes 8.1 years, and so on. Okay, so the question is, you are a NASA scientist and you're sending the satellite off to do this. What is the fastest possible route you could find? Because obviously, I mean, why not take the fastest route, right? The faster the satellite completes its mission, the faster you can analyze the rock samples. So again, the reason I'm showing you this example is because this is a traveling salesman problem. A traveling salesman problem is just a catch-all term for any sort of traveling problem where you want to minimize the cost of your trip. And cost might mean literal cost, like monetary cost, or cost might mean time cost, or gasoline cost, or emotional cost, I don't know. So cost is also a catch-all term. Here's another example. This figure shows 7 locations on Mars where NASA scientists believe there's good evidence of finding, or a good chance of finding evidence of life. So they've charted out these spots, and in this case, what this table is telling you is that to get from spot A to spot G takes 7,500 yards or something. It never gives me the units here. Okay, so I forget what the units are. So let's just go with yards. To go from A to G is 7,500 yards, from A to H is 5,000 yards, from A to I is 2,800 yards, etc. So again, you could take these 7 dots here, draw edges between everybody, and label the edges with the distance cost, and then you can ask the same thing. You're going to tell this rover what to do. You want it to minimize the amount of distance it travels. Right? The more distance it travels, the more wear and tear is going to be on it. Right? The more time it's going to take, probably. But anyway, you're trying to minimize distance. So how do you do that? Do you go from G to H first, or from G to I first, G to N first, whatever? How do you plot a route that minimizes cost? Yeah, so this just says everything we just said. So you want to make sure you plan so that you're minimizing the amount of distance. This is in miles. Okay, that's a really long ways. Okay, whatever. But the point still stands that you want to find the shortest possible route where the rover travels through all 7 of these sites exactly once. You don't want to visit site I twice. Why would you visit it twice? You visit once and collect your sample and move on. So in each case, the problem is to find a tour. And here, tour is a technical term that means a trip that starts and ends at a designated site, and you visit each of the other sites exactly once. So I should have put the word exactly in here, but only one time do you want to visit another site, right? So if you're collecting samples or whatever, you've already collected your sample from site A, so why go back? And furthermore, you want this trip to be optimal so that it costs you the least. And again, cost might mean monetary cost, or it can mean distance cost or time cost, whatever. So any problem that shares these common elements, you have some sort of traveler, you have a set of destination sites, you have some sort of measure of cost that tells you how much it will cost you to get between two given sites, and you need to tour all of the sites. And furthermore, you want to minimize the total cost of the tour. Anytime you have such a thing, it's called a traveling salesman problem. Traveling salesman problems are a big deal. Okay, so pretty much any delivery company, so think about Amazon delivering packages, FedEx, UPS, whatever, every single day, each individual driver has to solve a traveling salesman problem. They're going to go to like 30 different sites, right? 30 different houses or whatever. And they want to travel to each house so that their overall trip is optimal, if possible. And again, optimal means different things. Maybe the drivers want to minimize time. Maybe they want to minimize the amount of gas used. And these two things might be distinct, right? But whatever. Every single day, Amazon is trying to solve a bunch of traveling salesman problems, one problem per delivery driver. Okay, so these come up all the time in the real world, so being able to solve them is incredibly important. So here's another example. A school bus picks up children in the morning, drops them off at the end of the day at designated stops. Each stop is a site. So on a typical school bus route, there might be 20 or 30 such stops. So in this case, your school bus is your traveler, and the stops are the sites. And what you want to do is minimize, let's see. It doesn't tell you what you want to minimize. Oh, time of travel. Okay, so now we're thinking of time as a cost. So the school bus wants to minimize the amount of time it's on the road. That's a traveling salesman problem. So every single day, every single school bus, right, is solving a traveling salesman problem. And presumably, the school district has hired a mathematician to try to solve that problem for them, right? But again, these kinds of problems happen all the time. As I already mentioned, delivery companies like UPS and FedEx are always dealing with traveling salesman problems. This is an interesting one. In the process of fabricating circuit boards, tens of thousands of tiny holes must be drilled in each board. So if you think of each hole as a site, and the laser that drills the holes is the traveler, here again you have a traveling salesman problem. If you want your laser to drill all of these thousands of holes optimally or efficiently, the order in which the holes are drilled matters, right? The order in which the holes are drilled should be such that the entire drilling sequence, which now we're thinking of as the tour, is completed in the least amount of time. This is a very difficult traveling salesman problem to solve because there are tens of thousands of sites. But anyway, so drilling holes in a circuit board is a traveling salesman problem. And again, this is an important problem because if you are a company that's in charge of making these boards, these circuit boards, the faster you can make them, the more profitable you will be. So you really need to take time to think about, how am I going to plan my route through these tens of thousands of holes in an efficient manner? Here's another example just real fast. You want to go like run errands and you have to go to a bunch of different stores, a bunch of different sites. Here they are. So again, you want to navigate these destinations optimally, and when gas was cheap, time used to be the key cost variable, but as the price of gas goes up, people now are more likely to be looking for a tour that minimizes total distance traveled or trying to minimize the amount of gas they use, whatever. And by the way, minimizing time won't necessarily minimize the amount of gas you use, okay, because you can sometimes find longer routes that burn less gas, depending on how you drive. Longer in terms of distance or time. Okay, so every traveling salesman problem can be modeled by a graph, and in particular a weighted graph. And weighted just means you draw numbers on each edge, and that number represents a cost to get between two sites. So a graph such that there is a number associated with each edge, and the number is called the weight of the edge. The beauty of this approach is that the model always has the same structure. The vertices of the graph are the sites, the delivery sites, or the stop sites for the school bus, whatever. There is an edge between X and Y if there's a direct link for the traveler to travel from site X to site Y, and moreover, the weight of the edge is simply the cost. So if cost is monetary cost, then it's a literal cost, or you might write down time or distance or whatever. In this setting, a tour is a Hamilton circuit of a graph, as opposed to an Euler circuit. Okay, so what is a Hamilton circuit? We're going to get to this later, but a Hamilton circuit is simply a path that starts and ends at the same spot, right, because it is a circuit. A Hamilton circuit is a path that starts and ends at the same place, such that you visit each vertex exactly once. Except for the vertex you end at. Okay, you start and end at the same spot. So I suppose technically you're visiting that vertex twice. Okay, but again, a Hamilton circuit is trying to model what delivery companies do. If FedEx delivers a package to my house, they don't want to come back to my house later in the day. Okay, that's very inefficient. Why would they deliver one package in the morning and another one in the afternoon? They should just deliver both packages at once. So Hamilton circuits are modeling what a delivery driver does. He visits each delivery site exactly once. Okay, so how do we model traveling salesman problems with a graph? The delivery sites, or the visiting sites, whatever context you're in, are the vertices. You label each edge with the corresponding cost, and you want to find a tour through the graph that's a Hamilton circuit. And again, that just means a circuit in which you visit each site, or each vertex, exactly once. Okay, so what you're looking for is a Hamilton circuit that minimizes the total overall cost. So just like in Chapter 5 with Euler circuits, usually if there's one Euler circuit, there are a bunch of Euler circuits. So the same thing is true with Hamilton circuits. If there's one, there's usually a bunch of them. So your job is to find a Hamilton circuit that's not just a Hamilton circuit. You want to find one that minimizes the overall total cost. So I should say that this will make a lot more sense once we actually start doing things like this in section 6.3. But for now, this is the general setting. Okay, with all of that in mind, let's now move on to section 6.2, which just lays the groundwork for Hamilton paths and Hamilton circuits. So these are the concepts we will need to solve these traveling salesman problems. So in Chapter 5, as we've mentioned before, we discussed Euler paths and Euler circuits. So back in Chapter 5, the name of the game was to find paths or circuits that included every edge once, and preferably only once. So now we're going to flip that, and now we're going to discuss a seemingly related, but actually not really related, game. Finding paths and circuits that visit each vertex once and only once. And paths and circuits having this property are called Hamilton paths or Hamilton circuits if you decide to end where you started. So here are the official definitions. A Hamilton path in a graph is a path that includes each vertex of the graph once and only once. And again, if we replace the word Hamilton with Euler, we would replace vertex with edge. So that's the definitional similarities here. And a Hamilton circuit is a circuit that includes each vertex of the graph once and only once, except of course that you must end where you start. So that vertex, I guess, is visited twice. So on the surface, there's a one-word difference between Euler paths/circuits and Hamilton paths/circuits. The former covers all edges, the latter covers all vertices. However, it turns out that the theory of these two kinds of things is very different. Okay, so in particular, with Euler stuff, we had a very nice theorem that told us exactly when an Euler circuit or Euler path existed. And all we had to do was analyze the degrees of the vertices. So for example, if all of the vertices are even, then there is an Euler circuit. And if not that. If there are some odd vertices, then there's no Euler circuit. So we had a very nice characterization of when Euler circuits or paths existed. We don't have that anymore with Hamilton circuits and paths. Okay, they're just different. There's no sort of corresponding analogy between the theories of Hamilton stuff versus Euler stuff. So as soon as you focus on vertices rather than edges, you're just dealing with a different ballgame. So here's an example showing that. This figure shows a graph that has Euler circuits and has Hamilton circuits. So it's not too hard to find a Hamilton circuit. We can go A, F, B, C, G, D, E, A. And notice that we visited every vertex only once, except of course for A where we started and ended. So, okay, so let's do that again. A, F, B, C, G, D, E, A. Notice that we did not traverse the edge AD, right? We didn't do that edge. But that doesn't matter now because we're not dealing with something Euler. Euler circuits are where you care about going to each edge exactly once. But for a Hamilton circuit, you don't care about visiting every edge. And in fact, usually you won't visit every edge because that would be inefficient. You only wanted to visit each vertex once and only once because, again, each vertex might represent a delivery site. So once you've been to D, why would you insist on traversing this edge if you don't have to, right? Why would you insist on traveling between A and D if it's cheaper to go from D to E and then E to A? Okay, so notice that if a graph has a Hamilton circuit, then it automatically has a Hamilton path because circuits basically are paths, right? You can just truncate the final edge from it. So in this last example here, we did what? A, F, B, C, G, D, E, A. Well, if we just didn't walk that last edge here, if we just stopped at E, that's a Hamilton path. So we haven't started and ended at the same spot, but we have visited each vertex exactly once. So contrast this with Euler circuits and path. If a graph has an Euler circuit, it can't have an Euler path, okay, and vice versa. So the difference between them was that for an Euler circuit, you needed no odd vertices. For an Euler path, you needed exactly 2 odd vertices. So this figure shows a graph that has no Euler circuits, but does have Euler paths, right? So what can we do? C, D, E, B, A, back to D. That visits every edge. So has an Euler path, but has no, has an Euler path, but has no Hamilton circuits. I misspoke, sorry. So there are Euler paths, but no Hamilton circuits. So the reason you can see there's no Hamilton circuit is okay, so let's decide where we're going to start. Suppose we start at A. Okay, if we're going to start at A, then we have to visit every other vertex. So let's just visit B first. So walk here, and then go down to E, and then we have to go down to D. And then since we must visit every vertex, we have to go to C. Oh, but we have to get back to A, don't we? So we'd have to go back to D. But that's not allowed. You're not allowed to visit a vertex more than once. So you might say, okay, well, let's start at B. Well, the same thing will happen if you start at B. You can go whichever direction you want, like down or over this way, but you're going to end up at D. Once you're at D, you have to go to C, and then you have to go back to D. Okay, so it doesn't work. What if you start at C? If you start at C, then you must go to D, and now to get back to C, you're going to have to visit D again, and that's bad. It's not allowed. So there's no Hamilton circuit here. But notice that there are Hamilton paths. I mean, you can start at C and then go like that. So C, D, E, B, A. That visits every vertex exactly once. Okay, so no Euler circuits, but does have Euler paths. No Hamilton circuits, but does have a Hamilton path. This figure shows a graph that has neither Euler circuits nor paths because it has 4 odd vertices, but has Hamilton circuits. So, for example, how would this go? A, B, E, C, D, A. Back to A. There's a Hamilton circuit. Also has Hamilton paths. You can go A, B, E, C, D. So basically what these examples are showing you is that just because there are Euler circuits, you don't really know anything about whether there are Hamilton circuits or Hamilton paths. And just because you know there are Hamilton paths, you don't know anything about Euler circuits or Euler paths. So essentially the reason that we're showing you these examples is because you might think that things we did in Chapter 5 would translate to Chapter 6, because all we've done is change the focus from edges to vertices. Unfortunately, that's just not true. There's really just nothing we can take from Chapter 5 into Chapter 6 that would be useful, except for the concept of graph, of course. But anything to do with Euler stuff just doesn't matter anymore. So here's another example. It has no Euler circuits but has Euler paths. But this example has neither Hamilton circuits nor Hamilton paths. So how do we know it has no Hamilton path? Well, remember how in this previous example here, the fact that C had degree 1, that was bothersome, right? That was troublesome because basically if you wanted to ever get back to C, you had to travel through D twice. And that meant that you broke being able to have a Hamilton circuit. Right, so if you start at C, you got to go to D, and then you leave, and you have to come back through D, which means you visit D twice. Notice that in this example, we have two vertices of degree 1, G and F. Those are both troublesome. Those are essentially what makes it impossible to have a Hamilton path. So suppose you were looking for a Hamilton path and you wanted to start at F. So you start at F and go to B, and now you can't come back to B because you're only allowed to visit each vertex once. So let's go from B down to C, and then we have no choice but to go to D, and now we have to visit G, don't we? But once we visit G, we have to come back to D, and we visited D twice. That's not allowed. So we can start at F again and go this way to A, and then down to D, and then over to E, and back to B. That's bad. You visited B twice, etc. Basically, there's no way to visit both F and G without visiting either B or D twice. So you can't have a Hamilton path here. So this has no Euler circuits, no Euler paths, no Hamilton circuits, no Hamilton paths. Okay, so you can build all sorts of examples, and they're in your book, showing that, as I said before, there's really, like, just because you know things about Euler stuff doesn't mean you know anything about Hamilton stuff, and vice versa. So this table summarizes all that. Sometimes you have an Euler circuit but no path, and you get, Hamilton stuff that does whatever, right? Yes, no, yes, 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 no, no, yes. There's just no predicting anything. Yeah, so this slide just says what I just said. We had some theorems for Euler paths and Euler circuits, so you think you might just be able to translate those theorems into Hamilton circuit and paths theorems. So you'd think we could take section 5.3 and just tweak those theorems and, replace the word Euler with Hamilton, but you just can't do that. It doesn't translate like that. So there really are no such theorems. So section 5.3, where we had these really nice theorems that just said, look, if all the vertices are even, Euler circuit. If two of the vertices are odd, Euler path. If more than two vertices are odd, nothing. Theorems like that don't exist for Hamilton paths or Hamilton circuits. It would be nice if there were such theorems, but there aren't. There's just no easy way to look at a graph and decide whether or not there's a Hamilton circuit or Hamilton path. Oh, okay. That ended earlier than I thought. Oh, okay, so I thought we were moving on to section 6.3, but of course we are not. Okay, so the big takeaways from this video were now we're focusing on traveling salesman problems, which means we're focusing on vertices rather than edges now. That's the change you make when you go from studying Euler circuits and paths to Hamilton circuits and paths. So before we move on to section 6.3, you must be comfortable with the idea of a Hamilton path, which is simply inside of a graph, you visit each vertex exactly once now. And you don't care about visiting each edge exactly once. You don't care about edges at all anymore. All that matters is visiting the vertices. And you would think that making that small change from edge to vertex, from Euler to Hamilton, you would think that that wouldn't be a big deal. That maybe chapter 5 stuff just keeps translating through, But that's not the case. Being able to find Euler circuits and Euler paths has really no relation to finding Hamilton circuits and Hamilton paths. So, in the next 3 sections, we will be focusing on finding Hamilton circuits and Hamilton paths, and mostly just Hamilton circuits. The reason we're going to focus on that is because, let me just return to these pictures here, this traveling salesman problem right here, what are you trying to find? You want to start at Earth and end at Earth and visit each of these other moons exactly once. So you're searching for a Hamilton circuit that starts at Earth. In this picture here, what do you want? Well, you're starting and ending at Willie's hometown, A. So you're looking for a Hamilton circuit that starts and ends at A. You are not looking for an Euler circuit, because if these represent roads, or air routes, why would you insist that he travel every single road or every single air route? That makes no sense. What you want is for Willie to visit each vertex once, but you don't care about visiting each edge once. That would be a very weird restriction to put on Willie. And in this picture here, I forget if we have a start point, but let's just say we're starting at W. That's where we drop the rover off, right? We are trying to find a Hamilton circuit inside of the graph that we could overlay on top of this. You want to start and end at W and minimize the amount of distance that the rover travels. Okay, so I haven't given you a way to solve any of those problems, right? I presented you with 3 real-world traveling salesman problems, and I haven't said a thing about how you would solve them. All I've told you is that you can't use Euler methods to solve them. Okay, so the next 3 sections will be dedicated to solving, like, you're the NASA scientist, how do you start at Earth and end at Earth and minimize the amount of time traveled here? So that's where we're going next.